All right. So today we'll go towards different other topics that we have stipulated for the day. So we will see different functions related to Numpy and Numpy arrays, and we'll do some matrix calculations and manipulations, and then we'll see some applications. Okay, with Numpy. Basically, how to solve a linear equation with Numpy. This one use case that we'll see. We'll try to see and do some kind of very basic image analysis as requested yesterday, if we get some time. All right. So that's the plan. I'll just write it down here. Then we have Numpy applications like solving a linear equation. Numpy. We try to see the image analysis as well. Okay. Let's start with a few of the functions that we have that we can, basic functions that we have with Numpy. All right. So to start with, let's basically see first things first. Import Numpy. Right. We have imported Numpy. Always, when you start a new program or a new Jupyter notebook, you have to import Numpy. Right. So what we'll do is we'll start with taking one of the we'll create an array using the full maybe a full function or otherwise, and we'll see how basically it looks like, just to revise one, right? So let's say array one, how to use full np dot full, and then we basically write say 4,3 or a 5,5 matrix, right? And we provide a value to it. Let's say we give 3 as a value, and we see again, let's say we provide an in32 data type to this. Okay, d type equals to print the array one. We get 5 cross 5 array with value 3 created, a 2D array, right? I'm not able to hear you. I'm able to hear. Okay. Anybody else not able to hear? Okay. How they will hear if I say that, right? So majority of the people can hear me? Can hear. Okay. Yeah. Thanks. Thanks, Mary, for the advice. All right. So this is how a full function works, right? We get a 2 cross 2 matrix, and with 3 filled as all the elements of that Numpy array. Right now, there is something called a identity function. Okay, or how to get an identity matrix. What is an identity matrix? Can anybody tell me what's an identity matrix?
Diagonal is 1, other indices are 0.
Okay. So the diagonal is 1 and the other elements are 0, right? That's what an identity matrix is. And it also should have, is it mandatory to have a square matrix? Like 3 cross 3, 4 cross 4, 5 cross 5, 2 cross 2? It's of size n cross n, right?
Right. It should have diagonal.
Yeah. So it's basically a matrix which gives you diagonal as 1 and others as 0. So in Numpy, it's pretty straightforward to get an identity matrix using an identity function. So np.identity, and we provide, let's say 4,4 is the shape that we provide as the first uh, argument, how we provide the full function. And since, sorry, my bad. We don't provide like this, my bad. We just provide 4. This basically, it gives you the value of n, and it creates an n cross n matrix. Okay. So this guy will actually create a 2D n cross n matrix, basically n cross n identity matrix. See, this is a diagonal. This is called a diagonal, right? So let me draw. So 1, 0, 0, 0. 4 cross 4 means 4 rows and 4 columns. And this is called the diagonal, the main diagonal of this matrix. And in identity matrix, the main diagonal values are 1, and rest all other elements are zeros. Right? This is what a identity matrix is, and this is the function that is used to create a identity matrix. Right? Here, if you see again, the default data type of each element is basically a float 64. You can just check array2.d type, and you get float 64. If you want, you can have your an integer value as well. You can simply give d type equals to np dot int 32 or 64, depending on what you want, and you get an integer here. Right? You also can give a boolean as a data type. So what do you think will be the identity matrix value if I give the data type as boolean?
So if we will take each row, it should be something like first row true, false, 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 second row false, true, false, false, something like this maybe.
Yes, right. So wherever there is 1, basically the main diagonal will have values as true, because 1 is if you see 1 is represented as true and zeros are represented as false, so it will be the main diagonal would become true, other elements will become false. All right. Hey, sorry, am I audible?
Yes.
Okay, sorry. Yeah, so yes, the main diagonal will be true. You see here clearly, and the other elements becomes false. This also can be done. All right. All right. So this is what identity function looks like and how it works. We have another function called a I function. Okay. What an I function do basically? It's similar to an identity function. Okay. Let's do a help on np.identity. If you do an np.identity, if you see the first argument, it takes as only n, right, which we pass here. So what this n represents, it's an integer value that takes the number of rows and columns. Basically, if you provide n, it gives you n cross n output, a 2D array always. Right? An identity array is a square array with ones on the main diagonal. Right? That's what it is. It's a square array. Right? So it only takes the value of n and it just creates an n cross n matrix on an array, right? But in case of I, let's do a help on I. What happens here is, if you see here, you get, yeah, it takes two values, m and n. Basically, it's taking both rows and columns, right? So I returns a 2D array with ones as diagonals and zeros. Yeah, I also is the same, but the difference here is I will not take only one n. It will not be a square matrix, right? It can have a rows and columns not same, right? In identity matrix, rows and columns were same. In I, rows and columns can be different values, right? Also, there's a parameter called k. Right? This parameter or argument, basically we can specify which diagonal to be 1. Okay? In the case of identity, the main diagonal will always be a value 1. The elements of the main diagonal will be 1. But here in I, we actually can decide which diagonal to be 1. And by default, the value of k is 0. It's a default argument, which basically makes the main diagonal as 1. And we'll see how we change the value of k, positive and negative both sides, and how the diagonal values gets changed. Okay? So let's see that. So we simply do np dot I, and I give 5. Okay. What happens here is, if you don't give the columns value, it creates a square matrix. Okay. If you see here, if m is optional, if m is not given, it defaults to n. So it creates an n cross n matrix, just like identity matrix. Looks like it's classic from linear algebra. I still remember something. Yes, definitely. Then it is, right? So if you see here, if we give only value of n, the default value of m also becomes 5, as same as n, and it gives you a square matrix, and the main diagonal becomes 1. Now, the first difference we'll see with identity matrix is you can give the value of m as well, right? Which means value of n is 5, the number of rows is 5, and the number of columns is 4. So if you do this, see here, what happened here is, so 5 rows and 4 columns will be created. So 5 rows means these will be 5 and columns will be 4. So, and we have not given the value of k to anything. K value is by default 0. It means it will have the identity, basically the value of main diagonal will be 1. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And the fifth row will be 0, 0, 0, 0, because you can't extend further, right? The number of rows are 4, columns are 4 only. If the number of columns were 5, then we would have a 1 at the 5th place, right? 5, place, this place. But since we only have 4 columns, the diagonal stops here. Okay? So this is the main diagonal. It's not a square matrix. Okay? Still, this is the main diagonal. If you see here, this is the main diagonal that we have, right? With 5, 4 matrix. All right. Now, clear this off. For example, we take np.I, and we basically create a 5 cross 5 matrix, and we give the value of k to 1. What happens here is, and let's take the change the p type as well to integer so that we get a clean output. right? So now not the row one, the column. It shifts itself one place above the main diagonal. Okay, so what happens here is k equal to 1 means positive 1. This is the main diagonal. If I point it out as this as main diagonal, k equal to 1 means move one place ahead, means like this above, or it increases the diagonal starts at column number 1, row 0 and column 1. This is where the diagonal starts. Okay, in case of plus 1, right? If it was k equal to 2, the diagonal would have moved 2 places above. So one place is this, the second place is this. This would have been the diagonal with values 1. Similarly, if we have k equal to -1, it goes down, right? In this terms, it will be row 1, column 0. In case of minus, the row value increases, the column remains column 0. Case of plus, row value remains the same, column gets increased. Other way to visualize is it goes below the main diagonal. So -1 means one place below the main diagonal. So this will become your this diagonal will become have elements value as 1. So let's see that as well. Or let's take -2 as a value. So if you give -2 means this is the main diagonal. 2 places below the main diagonal. This is 1 and this is 2. So these 3 will be identity. I mean values as 1 as elements. Making sense?
Yes.
All right. Now let's do one thing. Let's see one more function called diag. This function basically is used to get the diagonal of the matrix. Okay, so the main diagonal, right? So what we can do is, let's say for example we have an array 3, for example, and we create np.random rand n 5,4, for example, and we print this array. So this is the 2D array, and with these elements of shape 5,4. Now, what will this diag function will do basically? So we can do np.diag, and we pass the array to it. All right. So if you see here closely, the main diagonal values are, this is the first element, this is the second element, this is the third element, and this is the fourth element. The diag will give the main diagonal values as a 1D array here, right? If you perform this diag functions on 2D array, right? So let's take the definition, see the definition of this. Extract a diagonal or construct a diagonal array. Okay, either extract it or construct it. Right? In this case, we have extracted a diagonal from a 2D array. So it takes a 2D array, returns the kth diagonal. Either if V is a 1D array, right? If the array is a 1D array, it returns a 2D array with V on the kth diagonal, basically. And what the value of k? Again, the value of k is 0 by default. But if we give k equal to 1, so it gives you the one place above the diagonal value, main diagonal value. So now this is the main diagonal. If you give k equal to 1, it goes to the one place above the main diagonal and gives you that value. If you give -1, the values of the next -1 diagonal will be given. The diagonal below the main diagonal. Right? So that's what the value of k is. You can just check it here. K equal to -1. So basically we get minus 0.55 minus, sorry, 0.55 minus 1.00, something of that sort. If you see this, this is what we are getting. One place below the main diagonal. Right? All right. Let's see some other functions. Let's see some of the maybe some statistical functions here. Okay. So first of is sum function. Okay. So sum function will do nothing but adds the, so let's take np dot a range. Let's take a range from 10 to 15. So A will be a 1D array with 10 to 14. If I do np dot sum and give A1, I get sum of all the elements of the array. Right? Now let's take A2. I create a 2D array using, let's say, np dot I. And here we give, for example, 3, 4, 4, 3 mnn value. Then k value I give 1. Okay, and whatever, right? The default data type. So I get this. Right? So now I can do a np dot sum of A2, which gives me 2.0 because only 2 elements are here, 1 and 1, others are 0. So I get 2. So sum function gets the sum of all the elements in the Numpy array. Okay. All right. Let's move towards some other manipulations related to Numpy arrays. So for example, again, I'll create A3 and we have np dot array. All right, we have, let's say, for example, 1, 4, 5 minus 3. A4 is equal to np dot array 4, 3, 0, and 8. Right? Now, can I perform, we have seen this yesterday, a glimpse of this. Can I perform A1 plus A2? Sorry, A3 plus A4. So we can perform this, right? And basically, if we do this, each element gets added to the, each element of A3 gets added to the each element of A4, right? So 1 gets added to 4, 4 gets added to 3, 6 gets added to 0, minus 3 gets added to 8, right? Now, in this case, np dot array, let's say we have 4, 7, and 0. If I try to add a Numpy array A3, which is a 1D array with 4 elements, and A5, an 1D array with 3 elements only, it says the shapes are not matching. It could not be broadcasted together with shapes. So for addition of 2 Numpy arrays, the shape should be same. Right? In case of a 2D array, right? Let's say in case of a 2D array, we had a 2D array here. No, A2. A2 was a 2D array. Let's create, let's overwrite A1, and I create np dot I. This is 4, 4, 3. Again, we create a 4, 3 with I, and we get a different identity matrix. So what we can do is here we can do A1 plus A2, which actually works. What happens here? It actually adds the corresponding elements to each other, right? So one gets added to 0, so we get 1. Here one gets added to 0, we get 1. This one gets added to 0, we get 1. This one gets added to 0, we get 1, and this one gets added to 0, we get 1. Other places it's all 0, so we have 0 at all the places, right? Again, the condition here is the shape should be same. Now, for example, I have, let's say, A6, which is np dot I 3, 4 instead of a 4, 3. I try to add A1 with, let's print A6 first. A1 plus A6. The operands could not be broadcast together because the shapes are different. So for adding two NumPy arrays, the shape of the array should be same. Making sense?
Yes, sir.
All right. Also, the same behavior can be achieved, this behavior can be achieved using a function called add, provide A1 and let's say A2. We get the same functionality as A1 plus A2, right? All right. Now we have the same as subtract as well. A1 comma A2. So A1 minus A2 happens if the shape is same. Again, the shape should be same for subtract as well, right? Now we have A1 and A2. Again, I print it. There's another function called np dot multiply A1 comma A2. What do you see as an output? All are 0.
Yes, all are 0.
What is happening? So it is clear that this is getting multiplied by this. This is getting multiplied by this, and so on. So this is not matrix multiplication, right? Or it is not the dot product. Is it the dot product? Do you know what a dot product is? Okay. If not, we'll see that. So what is happening is this multiplication operation is basically multiplying each element with other. Okay. All right. So even for this, the matrix multiplication as well, the shape should be same. Okay. Multiplication as in each element gets multiplied with other. Now let's see something called a dot function. What does it do? Sorry. Okay. Now we had a A1 as the same 4, 3 matrix. A2 also as a 4, 3 matrix. But what happened when we try to do a dot? It's giving an error saying shapes 4, 3 and 4, 3 not aligned. 3 dim 1 not equal to 4 dim 0 means the dimension 1, this should be actually equal to this guy. The column of the first array should be equal to the row of the second array. So let's see what dot product is. So a dot product of a matrix is written like this. So let's say we have one matrix with 2, 3, 1, 7. This one matrix dot product of, or let's not take this, 2, 3, 0, 1, 7, 1. This is a 2, 3 matrix. Right? Yeah, again, yes, it's a rule of linear algebra for multiplication of matrices. Yes. Multiply two matrices in algebra, right? That's called a dot product. So the row, this column should be equal to the second array's row. So this has to be 3. You can have 3, 2. Then it will be able to multiply. So we should have 3 rows. So let's write like this: 1, 2, 3, 0, 1, 2, 2, 1, 0. So now this is 3, 2. If you multiply this, and we'll see how this works is, so what happens in a matrix multiplication, usually always dot product. This guy, so this row gets multiplied by this column. So let's name it as R1, R2, C1, C2, C3. This is R1, R2, and R3. Oh, sorry. This has to be 3, 2. This is C1 and C2. Now, R1 gets multiplied with first C1, then with C2. And whatever the value is there will come on the, okay, let me do this and show you. So how this works is, the output matrix should look like this. 2 gets multiplied by 1. It's 2 multiplied by 1 plus 3 multiplied by 2 plus 0 multiplied by 3. 0 multiplied by 3. And that is why the number of columns of this first array should be equal to the number of rows of the second matrix or array. This. So this R1 gets multiplied with C1 first, and this is the first element of the matrix. And this is 2, 3. The second is 3, 2. The output will always be, output matrix will always be 2, 2. So R1 gets multiplied by C1, then R1 gets multiplied with C2. So 2 gets multiplied with 0, 3 gets multiplied with 1, plus 3 gets multiplied with 1, plus 0 gets multiplied by 2. So let's write 0 for that. Then this is done. Then we do the same thing for R2. R2 gets multiplied by C1, then R2 gets multiplied by C2. So 1 multiplied by 1 plus 7 multiplied by 2 plus 1 multiplied by 3. This is done. And it's multiplied by same thing multiplied by C2, 1 multiplied by 0 plus 7 multiplied by 1 plus 1 multiplied by 2. So here the output will be 2 plus 6 plus 0. So it is 8. 0 plus 3 plus 0. This is 3, 1 plus 14, 15 plus 3, 18, 0, 2 plus 7 is 9. So you get a matrix as 8, 3, 18, and 9. Right? Let's see this. So let's say A1 equal to, or M1 equal to np dot array. So we have 2 comma 3 comma 0 comma 1 comma 7 comma 1 as M1, and M2 as np dot array 1 comma 0, 2 comma 1, 3 comma 2. And we do np dot function a1 comma a2, sorry, m1 comma m1, m2. We should give a 2 cross 2 matrix with the values 8, 3, and 18, 9. This is what is the matrix multiplication in linear algebra, right? So this dot method, dot method, is used to achieve that. Clear? And to achieve this, the row of the, the column of the number of columns of the first matrix, which is 3, should be equal to the, so the row of M1 should be equal to the column of M2, and the resultant matrix will always be the row, sorry, the column, sorry, the row of, I'm really sorry, this is should be the column of M1 and the row of M2, and the resultant matrix will be the row of M1 cross column of M2. And this is how it is calculated. Clear? And this whole calculation is done by a single line using np dot dot. All right. I hope this is clear. I'll move on. So let's take A1, A2, what do we have? A3. Let's take A3. Okay. There are other functions as well associated with arrays. You can find the statistical, we could perform statistical operations also on the Numpy array. For example, np dot, or yeah, np dot var, okay, or you can do a mean of A3. What this does is it actually calculates the mean of the array and prints that and returns the output. np.mean. You can also do np.var, which is the variance, right? Then we have the standard deviation also. Okay. And you also have median as well, right? Okay. Instances. As I remember, the matrix multiplication also was needed for a little decrease measurement of matrix, right? Yeah. So matrix multiplication is required for multiple things, right? It has multiple use cases. So whatever it is, it can perform simply in a single line using numpy dot. That's what the whole point of showing basically this method or this function. Right? All right. You also can perform, let's say, for example, you have this matrix M1. There's a function called transpose. Okay, if you remember transpose, np dot t, I guess it is. I'm not sure. No, it directly works in the array, I guess. This is the attribute. So what happened here is, what is a transpose? A transpose is something, it transposes to this matrix. The rows becomes the column becomes the rows. So 2 and 1 becomes the columns. This row becomes the column. 3, 7 becomes the other column. 0, 1 becomes the column. And these were the rows. 2, 3, and 0 values becomes the, sorry, this column becomes the rows. Okay. This is the transpose or transposition of matrix, can be performed using .t attribute. Okay. All right, what else we can see? We've seen the Boolean, yeah, we have seen the Boolean indexing as well. Let's see another function. It's a linspace function. Okay. What this linspace function do? Basically, let's do a help on this and then we'll take an example on this. So what it does is it takes multiple arguments. We'll focus on these three first. Okay. So there is a start argument, stop argument, mandatory arguments, and then we have some default arguments. So this is num value, which is 50. So what it returns is it returns a evenly spaced number between over the specified interval. The interval is start and stop. So it includes both start and stop values. So returns a num evenly spaced samples. In this case, 50 evenly spaced samples calculated over the interval start and stop, both included. Endpoint of the interval can optionally be excluded. So endpoint is true by default, means it includes the stop parameter, right? If you make it as false, it will exclude the stop parameter. It will stop before the stop parameter, right? It will not be included. Okay, and let's see an example with this. So for example, we do np dot linspace, and we give the starting point as, let's say, 1, and the ending point as, or the stopping parameters as 10. So by default, the num value is 50. So it will give you 50 samples between 1 and 10, both included. So it creates a 1D array of 50 samples, evenly spaced 50 samples between 1 and 10, both included. Right? So we can assign it to, say, array 1, and we can print array 1. We can do array 1 dot size, and we get 50 samples. Right? And just to confirm the shape, it gives you 50 comma, which means it's a 1D array. Right? So this is what it gives. And we can change the values as of num as well, which means let's say array 2 equal to numpy dot numpy line space. Let's say I want from 20 to 30. I want num equals to 30 samples. So between 20 and 30, it will give me 30 equal samples, right? 30 equally, spaced samples. All right. Now I just remembered we had another few other functions, some universal functions with arrays again. So let's say we have A3. So what we do is we do np dot sqrt is a function and provides with A3, which basically calculates the square root of all the numbers. If you see here specifically for -3, it gives you a NaN value. This NaN is nothing but to represent not a number. Why? Because you cannot do a under root or a square root of any negative value. It's a complex number, right? Or you can say the imaginary number. So you can't do this. So the sqrt function is not capable of doing it. So it gives you a warning as well here. And the value of sqrt of -3 is returned as NaN, or a number. Okay. For others, it calculated the square root. Then we have something called an exponential or exponential function, np dot exp. Yes, and we give A3. So what happened here? Okay, yeah. So it calculates the exponential of all the elements in the input array. That's what it does. All right. And we have seen others as well, some variance, mean, and other things that is kind of done, right? So we'll see some other functions as well and other manipulations as well, right? There is a function called reshape. What this reshape does, see the definition of this. It gives a new shape to an array without changing its data. It basically changes the shape of a existing array. Okay, let's see how it works. Okay, so you have to give the array for which you want to change the shape as and the new shape that you want. Okay, that's what it takes as an input. So for example, A3 we had, right? This is a 1D array. To a shape of it is giving you 4,1. Now you can create using reshape, not repeat, reshape, and you give the array A3 and you provide a valid shape for this. So can this 1D array with 4 elements be converted into a 2D elements of two rows and 2 columns each? So the shape, can its shape be 2, 2? Right? So see, it gets converted, a 1D array of shape 4, gets converted into a 2D array of 2, 2. So let me put it in, let's say 4, and A4 is this, and A4 dot shape is nothing but 2, right? Now let's say ARR equal to NP dot A range. Let's take 1 to 11. It gives you 1 to 10. So we have a 1D array of 10 elements. ARR of shape will give you 10 comma. NP dot reshape. Can it be converted into can array be converted into a shape of 2 comma 5?
Yes.
Yes, yes, okay.
Yes. Can it be converted into a shape of 5 comma 2? Right, which is possible again. Can it be converted into an array of 3 comma 3?
No.
You're right.
No. Yeah, by definition, it says that the data should be saved without changing its data. So it also means that it cannot lose any data, right? So basically, it is not, see, cannot convert a size 10 into shape 3 comma 3. You should, the shapes should be 3 cross 3 should be equal to 10 cross 1. If that is false, then it won't be able to convert. It's a value error. It won't be able to convert it. Now, for example, again, I take ARR1, NP dot A range 16. So we get 16 elements, 0 to 15, right? I can do reshape of ARR and 2 comma 2 comma 4. So it gives me a 3D array. Right? You see, this is a 3D array of shape 2 comma 2 comma 4. If I do a shape of this, I get 2 comma 2 comma 4. That's what we have. So 2 multiplied by 2 multiplied by 4 is 16. That's what we get here. Array 1 is of shape 16 comma 1. Sorry, 16 1, which is a 1D array. The reshape can only be done if the both the shapes of the resultant array and the existing array multiplies and gives the same result. All right. All right. So now let's see something which is called array concatenation. Okay. Array concatenation. So let's see concatenation between two arrays. So let's take A3, which is a 1D array, or and let's say the function is concatenate, sorry. And if we do array 1 comma array 2, see what happens. So it does not work. Why? Because we have to, I think the way I'm providing the values are wrong. So let's confirm that. Okay, yeah. We provide it as a single object, either an array or either a list or a tuple. So it concatenated both the arrays, right? A1 and sorry, array 1 and array 2. 1, 2, 3, 4, 8, 4, 0, 1. 1, 2, 3, 4, 8, 4, 0, 1. Right. Now let's see. This is M1. This is M2. So M1 is of shape 2, 3. M2 is a shape of 3, 2. Can we do a concatenation of M1 and M2?
I'm not sure.
No, we can't, right? Because it will try to basically concatenate these values as single elements. It basically will try to concatenate this row and add a row here in M1, which is not possible because the number of columns are not same, right? So this will not work. Let's take A1 and A2. I think, yeah, if you try to do np.concatenate A1, A2, this will work because these can simply be added here. This can go and add to A1 basically, and it gives you a new array. Does not change the existing A1 or A2. It gives you a new array with a different shape. The number of rows increases. So this is what concatenation is. Increases the number of rows. Why? Now see this. We have this. There is another parameter that we can use, and we can change the behavior of it, which is the axis. So what axis is? Axis is by default 0, and hence the number of rows are getting added. Okay. On the contrary, if we change the value of axis to something else, we'll see what the axis along the arrays will be joined. So array axis equals to 0 means rows. So axis along the rows, the arrays will be joined. Right? Concatenation will join two arrays along the axis. Which axis? By default it is 0, which means the rows. Okay. Now, if we change the value of axis, right? So let's take A1, A2 again, and let's say we do np dot concatenate, and we have A1, A2, and we change the value of axis equal to 1. See what happens. Axis equal to 1 is on the for the columns. Okay. So it adds the columns. Okay. So let's try to understand this. So for example, we have a matrix 2, 3, 0, 1, and we try to concatenate. I am using C for that, and C 2, 0, 6. To concatenate using axis equal to 0, which is by default is the case. So it will be this 3, 2 will be added on the rows, and 0, 6 will be added in the next row. So basically it will be 2, 3, 0, 1, then joining the other array 3, 2 and 0, 6. It becomes a 4, 2 matrix. If you concatenate using the axis equal to 1, so it will not join row wise, it will join in the column. So this 2, 3 and this 3, 2 gets added here, and right 0, 1 and this 0, 6 gets added here. This is the difference between axis equal to 0 and axis equal to 1. All right. I hope this is making sense.
So I have a question.
Yes.
In situation with this function, should we have the same number of columns such as a parameter, which should be the same for both matrices, or what?
Okay. Okay. Let's answer that. So let me remove this. Clear all. Now, so let's say you have a matrix 2, 3, 1, 0. try to concatenate axis equal to 0. Okay, this is axis 0. So row wise. In case of addition of rows, so 3, 2, 3, sorry, 2, 3, 1, 0, 0, 0. So how it will try to add is, it will try to add this 2, 3, 1 here. It will try to join it here, 2, 3, 1, right? Which is not possible, isn't it? Because the number of columns for the first matrix is 2. The number of columns for the second matrix is 3. If you try to add or join these two matrices along the rows, the columns are different. So here the columns should be equal. The column of the first matrix should be equal to the column of the second matrix. Okay, but in case of axis equal to 1, what happens? It joins like this, right? 2, 3, 2, 3, 1, which is possible, no problem. 1, 0, 0, 0, 0, again, which is possible. Now, in case of axis equal to 1, this is not necessary to have the columns should be equal for both, but the rows should be equal, isn't it? So if you have, let's say, another row here, 1, 1, 1, so there is no row for to be added here, to be joined. So for axis equal to 1, the rows, number of rows should be equal. Number of rows should be equal. For x equal to 0, number of columns should be.
Thank you, I got it.
Yep.
So axis is a key parameter for concatenation.
Yep. Cool. Any other questions, anyone? All right. Let's see another thing here, which is basically splitting. What splitting does is, let's take array 1. So we have array 1, which basically is from 0 to 15. The size of it is obviously 16. Right? Now I can do a split of this array. Okay? So np dot split, and I do array 1, comma. I want to split. Okay, split function will basically splits the array into n number of arrays depending on the number of split I want to do, and it should be equal splits. Okay, the split function should be equal splits. For example, these are 16 elements, so I can split the 16 array 1D array into 2 splits, which is 8 and 8. So I get a list of, this is a list of 2 numpy arrays with elements 8 each, because there were 16 elements got divided into 2. Equal division can happen, so it splits the array 1 into 2 arrays of equal elements. Now, for instance, we try to split array 1 into 3. This will try to split. Can you split array 1 equally into equal n equal arrays with, n equal arrays, right? No, right? Because 16 divided by 3 is not a whole number. You cannot have an equal division here. So this will give you an array. Array split does not result in an equal division. All right, this is how split works. Making sense? If it works, if you can make a split, it will create a list of numpy arrays. Those many number of splits it will create. So 2 is number of splits that you want. Okay. Again, you can do array 1, comma 4 splits. Obviously 16 divided by 4 is an equal split. You get a list of 4 numpy arrays splitted equally, and the sequence also remains the same. If you see the sequence, it remains the same, right? All right. In splitting, there is another function, but this is a different function, it works a little differently. So this is called array split. So how this works is, so let's do this. So array one again is of 16 elements. I try to do an array split of array one into 4. So it gives the same output as above. It equally divides the array one, which is of 16 elements, into 4 1D arrays of 4 element each. Right? Same as above. But the difference comes into when it's not able to create a equal array, right? A equal split. Sorry. I want to split array one into 3 splits, but it should work, right? Doesn't matter equal or unequal, right? So if you see here, it has actually created an array, 3 arrays. One, this is a 6 elements. This is of 5 elements. And this also is of 5 elements, right? Array split will not focus on creating equal splits or splits into equal division. Okay? It will not concentrate on creating equal division. Okay? It will simply create equal, sorry, those many number of arrays, right? How? How will the split be divided, right? How will be the, if it's unequal division, how the elements will be decided, which element will go there. So it has a formula which you can see using help. So if you see this array, blah, 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 how many indexes or sections you want. And again, x is equal to 0 is for row wise. Okay, we'll come to that. But the formula here is, if you read this, please refer the split documentation. It's exactly the same as split. The only difference between these functions is that array split allows the indices or section to be an integer that does not equally divide the axis. That's what we have seen already. But what happens in case of unequal length, right? For an array of length L, okay, that should be split into n sections. Okay? The length of the input array is L. That should be split into n sections. Let's say in this case 3 sections, right? And in our case L is 16. It returns L percentage or L modulus n sub arrays of size this, and how much remaining arrays of size 1 floor division n. So let's write in our case. In our case, L is 16 and n is 3. So what will it return? It will return n modulus n. So 16 modulus 3, which is 1. It will return 1 sub arrays of size this. Sub arrays of size, again, L is 16, n is 3. The floor division of 16 divided by 3 is 3. Is it not? No, sorry, 5. 5 plus 1. So basically, which is 6 elements, right, of size 6, means 6 elements will be there for one array. Isn't it having 6 elements of one array, 0 to 5? And the rest of the arrays will be of size L divided floor division n. So what is the rest? We wanted n, so it will be n minus 1. So 1 is already done, so we need 2 subarrays of size L divided by n, 16 divided by 3, which is 5. So 2 subarrays of size 5. 6 to 10 is 5, 11 to 15 is 5. Making sense?
Yes.
Yeah. So first I'll apply this one. how many arrays it can create, it will create. The rest of them will apply this formula. Cool. Let's move to a topic which we have already discussed yesterday in a very brief, okay, in a very simple terms. We'll move towards seeing how Numpy is faster than a list. So we'll try to see basically a program, and we'll see how much time it takes using a program on with a Numpy array, and same thing we'll try to do with a list and see how it is taking time with a list. All right, just give me a minute. Let's start. So what we're going to do is we'll see, we'll try to create do a dot product of some number of arrays, okay, for a higher number of arrays, and we'll see how much time does it take using a Numpy array, and similar thing we'll do using a list. For that, what we'll do is use a module called datetime to fetch the present time and start time and end time, and see how much time it takes. Okay, for that we'll import a datetime. From datetime import datetime. Okay, so datetime is a module, and this guy is also a function as well, I think. So if you do datetime help, yeah, sorry, it's a class, and this class has I mean, we can deal with we can get the system's date in particular format as we want. There are multiple functions that we can use with this. We can get a time zone and all those things, everything we can get it. But simply we'll take a time to start with, and then we'll see how it works. So first we'll start with how much time it will take for a Numpy array to do a dot product. Let's create A1. Sorry, any questions? Okay. Not array, let's use a range. So in A1 we have, let's say, 100 elements. A2 is a 1D array of, let's say, again 100 elements. Okay, and what we're going to do is we basically will run a for loop 100 multiplied by 100 times, which is 10,000 times, and do a dot product of A and B. Okay, so before that, start time equals to date time dot now, the present time we take, and we do whatever we want. Let's say for in range, so 100 multiplied by 100 is 10,000 times. We'll do, there's another way of doing dot product. You can do A1 dot A2. This also you can do. Okay. And after doing this, end time equals to date time dot now. So again, we get the present time, and we get the time for, let's say, time 1 equals to end time minus start time, and we just print the value of time 1. So I run this code. It takes around 0.28980 milliseconds. Okay? 0.02898 milliseconds. So let's try to do the similar thing with lists, right? So I have a list which I create using range, for example. So the same range 100, and I create the same thing L2, and we have start time. We take it from here, then we do some function, then we take the same code to get end time and time 2, time 2. So in between we do our functions. In this case, we have to write a code for doing the same thing with what we did with dot, right? Here we can't do a dot directly. So in that inside this, we will have out equal to 0, and for j comma k in zip of L1 comma L2, okay, out plus equals to, we have to multiply j with k. So, and then after doing this, we'll get the same result, and we'll see what's the time taken. You see here, the time taken is 0.47 seconds, right? Sorry, yeah, 0.47 seconds or 47 milliseconds, which is way bigger than time 1. So it is time 1 divided by time 2. If you do time 2 divided by time 1, if you do, is 16 times slower for this operation, right? So this I wanted to show to make an understanding that how NumPy is faster than a normal list, right? Any questions? So you can check with other you can do the same thing using NumPy, and you can do the same thing using list, and try to find out a time difference between them. Obviously, or mostly, almost every time, not almost, I think every time it will be NumPy will be faster than a list operation. Cool. Let's see something which is solving a linear equation, right, using NumPy. So this is one of the applications. If you remember, in linear algebra, we have some kind of linear equation with two variables, right? If you remember some kind of a problem like solve for x and y, right? So it can be simple as x plus y is equal to 30 to x, so minus 3y to 12. Okay. We have to solve for, we have to find the values of, find x and y. Okay. So basically we have to do some multiplication and then do a division and do a subtraction and all those things. So how to solve this mathematically? I'll just give you a revision for that. So let's say this is an equation 1, this is equation 2. So what we do is we try to remove one of them, and then first find the value of one of the either y or x, and then by substituting the value of the one variable, we find the second variable. So in this case, what we can do is we can multiply the equation 1 by 3, and we multiply the equation 1 by 3 throughout. We get 3x plus 3y is equal to 90, and what we do here is we add these two variables. So we multiply 1 by 3, and we do 1 multiplied by 3 plus 2. So in this case, this gets to 0. We get 5x is equal to, or let's make it simple. Let's make it 10. So this guy is 10. So 5x equals to 100, x equal to 100 by 5, which is nothing but 20. Right? And by substituting the value of x, we get the value of y. So x is 20, 20 plus in equation 1 will substitute 20 plus y equals to 30, and y equals to 20 minus 30 minus 20, which is 10. So x equals to 20, y equals to 10. This is how we solve it mathematically, right? So I'll just change it. This was 12. No, this was 10. Okay. So how to solve it using Numpy? Okay, pretty straightforward. It's not directly available in Numpy, but it is available in, let's say, for example, we have, okay. So these values are called any values related to x and y. These are called coefficients. Okay? So here the coefficient of x is 1. Here the coefficient of y is 1. Here the coefficient of x is 2. Here the coefficient of y is minus 3. Okay, and these other ones are the values, right, which it's assigns to. So either in algebra, there's another way of writing it using matrices as well, right? So you can write it as matrices, isn't it? So 1, 1, 2, minus 3, basically something 30 and 10, and using this also you can solve it, but we're not going to see that. But I just trying to remember that as well. So what we can do here is we can simply use NumPy, matrix of coefficient and others. That's it. So simply what we can do here is we can use a method which is available, which is np dot linalg. This is a linear algebra functions relied on blah blah blah. Basically is a function. It's a package, okay, available which is used for linear algebra related functions. Okay. So it has something called multiple functions. Okay, if you see here, it has a multi dot. It is a matrix power. Some decomposition values are there. Some how to find eigenvalues. We have some norms and other numbers as well. Okay, you have solving equations and inverting matrices. There are for some functions. There are few exceptions that is getting created. Well, some errors happen. This kind of the line ALG error exception occurs. So all the information you can get it here. Basically, in short, this is for linear algebra. This is the package available with NumPy for linear algebra. You can do multiple things here. So to solve a linear equation, we will use the solve function. Okay, we'll use the solve function. How? Basically, we'll use it is we'll see the help of, let's say, NumPy dot solve. See this, it takes A and B, solve a linear matrix equation or system of a linear scalar equations, computes the exact solution x of well determined that is the full rank linear matrix equation Ax equal to b. So basically it takes the first value as coefficient matrix, and the second is the ordinate or the dependent variables or the values. So what it means is it takes the coefficient matrix. Basically coefficient matrix, as I showed earlier, is nothing but it's a 2D matrix here, 1, 1 and 2, minus 3. And the values are a 1D array of 30 and 10, right? So we'll create that. So first what we'll do, we'll create coefficient. Let's create a variable called coefs, numpy.array, and we need a 2D array here, right? What? The coefficients. Coefficient for first equation is 1 x plus y. The coefficient will be 1, 1 and 1. Second one is 2x minus 3y. So coefficient becomes 2, minus 3, right? And the values becomes a 1D array is numpy.array, which is nothing but 30 and 10, I believe. 30 and 10, right? And this solve, so we will do result equal to np dot linealg dot solve coefficient, vals. Print result. Remember the result. It was x was 20 and y was 10. So it gives you x. First value is x, second value is y, because in that format only we have given the coefficients. So this is x, second value is y. This is the dependent variable of x. This is the dependent of value of y, and we get x equals to 20, y equals to 10. Making sense? Pretty simple, a single line. If you have code, just have to find the coefficient and the values. Cool. Any questions?
So I have a question, Manish.
All right.
Looks like we also could solve not two equations, but one equation, right? Such as with discriminant, something like this, but only with the Numpy help, correct?
Can you please repeat? I didn't get that. We are solving two equations right here.
Yeah, now we are solving two equations, but we are do we can solve one equation with Numpy?
We should be able to do, yes.
Got it.
It works. Yeah. All right. So next, we'll try to see on a very basic level. I think there was a request yesterday for image analysis to be done, right? So we'll just see how can we do it, and you can explore it, after the session. Okay. So how it works is basically we need a couple of obviously we need NumPy, but we also need some other what do you say, libraries for that as well. Okay, one is NumPy. Obviously, we have already imported. We'll use the matplotlib library. If you're not sure about matplotlib library, you can explore that as well. But for we will plot. Matplotlib library is used for plotting the graphs in Python. It's a library for plotting graphs. Okay, so we'll use that library to basically see our image. We'll plot the image as a graph. Okay, and for opening an image, basically we will use our library called PIL. PIL image library. We will be using it. Okay, so we'll just already we have NumPy installed. Sorry, imported. We'll import matplotlib as well. Matplotlib dot pyplot is what we'll import as PLT. This is one for plotting. The other one for opening, there's a library called PIL. From PIL, we'll import only two things. One thing is image. I think image only. Okay. So basically we do this, and simply what we do is we will create a NumPy array, open the image and create a NumPy array. Okay. So let me take an image. Oh, let's take this one. Just give me a sec. I'll download and put the image in the directory. So I do this, and basically I will use the NumPy array to open the image. First, we open the image. So my image equal to, I'll use the image class from the PIL, and sorry, that image dot open is a function that is used, and the python.emg png is the image that we will open. So what I'll do is I'll image, it is an image object. Right. So we have this image. Now, what we'll do is we'll basically convert it into an array, because that's what we'll do. Analysis. Basically, we will do some manipulations using NumPy arrays only. So what we'll do is this object will convert into NumPy array. So image arr equal to np dot simply array, and this image object, we can put it directly in this, and we get an array. If you see here, image array. So you get a array like this. Okay. So this is nothing but yeah, this is every image will have the pixel value, right, of R, G, and B. So this is what it gives you. Okay, this is what it gives. So if you see the dimension, basically 3D array, and why is it coming as 4 here? Should be 3 R, G, and B values. Should be 3 values here. I'm not sure why this value is coming, but anyway, maybe something the way it has opened the image, but it will work the same way. Let's move ahead. So what we're going to do is we basically will maybe, do some, minor changes like cropping the image, right? A very minor change will basically do some kind of cropping. In that case, what we're going to do is we'll just basically first create the figure size. We'll use the matplotlib now here. Okay, so the figure equal to, we create a figure to plot a plt.figure, and then we fix size, let's say. So these things are all matplotlib stuff, 8,8. Okay, and this is the figure size that we have, and we will, plt.show will do, and we'll give the image array. What happened? My bad. IM show, image show. Okay, so this is how it will be shown, in kind of a graph. Right? So what we're going to do is now we'll try to crop it. Okay? So how we're going to crop it is, now we know these are the coefficients, right? These are the matrices. So what we'll do is we'll do a slicing here, isn't it? If we get the sub array out of an array, it's kind of cropping it, right? Isn't it? So what we're going to do is, let's say cropped image is equal to at image array score array, and sorry, we'll do slicing. Let's say, for example, we take 100 colon minus 100 comma. It's 3D, so we do 3D minus 100, and the last one we keep it as it is. So we got cropped image. The spelling is wrong, but that's okay. Now we try to plot this. So you see, we have cropped it. So this is one of the examples of how we can basically now you can use using plt.save. There is a method called save with matplotlib. You can save this whatever image that you have, whatever plot you have in a image file. So simply you can manipulate it using numpy array. After getting the pixels as a array elements, you can basically play around. So what else you can do is you can basically so this is the simplest example I could have given you. You can actually change it's to a negative, right? I can change the value the image to a negative value. You can get you can rotate it to a 90-degree or a 180-degree, right? All those things you can do by manipulating the values of these values basically. Okay. So I'm not gonna go deep into it, but just wanted to give a glimpse and an application how basically you can do an image analysis using NumPy. All right. So I think that's what I wanted to discuss in these 2 days. Right. So any questions regarding anything?
It will be helpful if you give this notebook.
We'll share that. Okay. Then says, do I understand right? By NumPy, with image, we could prepare NumPy for deep analysis, for example. Yes, you can do analysis of this image as well, right? You can manipulate as well. So you convert this image into a pixel, pixel values, and convert that into basically a NumPy array. And whatever analysis you want to do on that can be done, right? And any modification as well can be performed. I think someone from the team would be joining in a while. So other questions, they will be basically, they'll be explaining about other platform and other things as well to you. And you can ask the other questions as well about recording and that sort. Then to give some examples of how NumPy could help with numerical data analysis. Okay, so see, we have so many functions and methods basically related to NumPy, right? So what we saw NumPy as a tool right now, right? So we saw NumPy as a tool, and these having so many methods, and which basically deals with matrices, right? So anything related to NumPy, anything that we do with NumPy, and we majorly work with numerical data on NumPy, right? So anything that you want to do an analysis directly can be done, right? So how will you basically try to want to create deal with trigonometrical functions, for example, or a linear algebraic functions, a Fourier transform calculation, right? Just giving mathematical examples of that. So anything and everything related to matrices can be done using NumPy, right? And by getting the data, which is basically the numerical data, if you are talking about that, we can actually have a convert it into an array, and then basically have it, check the size of it, check the shape of it, maybe do some calculations, mathematical operations, and we come to a conclusion that will it be suitable for our some kind of analysis or not. Let's say, for example, you have a sparse matrix, right? A sparse matrix is a matrix in which you have more number of zeros than a non-zero numbers in a matrix, right? So if you have some kind of sparse data like that, you can convert it into arrays and do some kind of operations in that to basically do some manipulations and get into do some analysis and get to a result, or get some analysis out of it. You can plot graphs using NumPy arrays, right? You can plot the arrays into a graph using matplotlib, for example, right? And then you can see that data, and then visually analyze that data as well, right? So I hope that makes sense. Using Numpy, you can fetch, you can do a slicing of the arrays, and only a small sect of data if you want to analyze, right? You can do that as well, right? So multiple things can be done. So you've tried to give a glimpse of Numpy and how it can be, useful in data analysis here. Yesterday example was good, how to take some matrix information from matrix table. Yeah, correct. So that is one of them, right? So maybe you have companies as a 1D array, and then you have a data in a 2D array, and you have matching of those into within each other. So some kind of Boolean operations can be performed, and it's very simple if you see, right? If you understand that, it's pretty simple. You don't have to worry much about how to basically perform fetch data for a particular company, right? As such. All right. So yep, I think thank you so much. I hope you enjoyed the sessions.